the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This video is dedicated to a high-level review of one-to-one functions and their inverses. And this is specifically meant for students at Cosumnes River College because our pre-calculus course at Cosumnes River College actually does not have inverse functions in the curriculum. However, I firmly believe that students should at least see inverse functions as a review in 370, which is our pre-calculus course. So if you're not a student at Cosumnes River College and you're watching this video, that's perfectly fine. It is just a review of a high-level, fast review of inverse functions. So if you know some of the, or most of the basic concepts, this might work well for you to kind of fill in some gaps or some holes. It's assumed that you have seen, just like pretty much everything in our pre-calculus course, it's assumed that you have seen one-to-one functions, inverse functions, you've found equations for inverses, you've graphed inverses, basically everything. But it's always nice to kind of see this review anyway. So let's go ahead and step through it. Excuse me. So inverse functions themselves, you have now likely seen and dealt with inverse functions through 2 full courses, probably 2, maybe even 3 full courses. However, this content is often a stumbling block for students and is essential to remember for calculus. So a very brief review is in order. Forgive my poor reading skills this morning. Sorry about that. So first thing you should remember is the definition of a one-to-one function. So this definition of one-to-one function tells us not only do we have a function, which means that each input leads to a single output, but each output leads back to a single input. So a function f with a domain D is called one-to-one if no 2 elements from the domain have the same image. It is like a super function. So not only does x sub 1 lead to y sub 1, but y sub 1 only leads back to x sub 1. That's kind of a way to think about it. So it's I always, when I think about it and I talk to students in class, I say the whole idea of a one-to-one function is that it's the best kind of function. It's sort of like arriving on a crime scene and seeing the result of somebody's action and saying, I know exactly who did it. Because you see the result and there's only one input that could have led to that result. So that's kind of what an invertible function is. I'm sorry, a one-to-one function is. I tend to call them invertible functions just because I have a habit of that. Now, this is the same thing as saying that f is one-to-one if each input leads to a unique output not shared by any other input, which I don't know if I'd say it that way, even though I wrote it that way. Something else you should remember from inverse functions or invertible functions or one-to-one functions is the horizontal line test, which just tells us a function is one-to-one if and only if any given horizontal line that you draw, in fact, any and all horizontal lines that you draw, intersect the graph at most once. And so if I were to draw really quickly, let's pretend as though, just for simplicity, that this is the x-axis, and I were to draw a function, that's definitely a function. Of course, there are horizontal lines here that intersect once. There's one, and here's another one. Well, sort of one, actually. I think I made that to where it intersected twice, but let's put a little bit higher there. There we go. But that's not what this theorem is stating. The theorem is stating that it is one-to-one if and only if all horizontal lines, any and all horizontal lines that you can draw, would intersect the curve at most once. Well, here's a horizontal line I can draw and it intersects the curve more than once, so therefore this is not a one-to-one function. On the other hand, if somebody comes along and again, here's the x-axis, if they draw a function and it looks like this, and let's actually make it more interesting. Now I'm thinking about it. Let's say it looks like this. Let's just say that it's domain restricted. Any and all horizontal lines I draw must be able to hit the curve at most once. So that horizontal line hits the curve at most once, so does this. And in fact, every single one that you draw will hit the curve at most once, even this guy down here. It doesn't hit the curve, so therefore it hits the curve at most once. 0 is less than or equal to 1, so it hits the curve at most once. So this is definitely a one-to-one function. Anyhow, that's really what that, just a reminder of the horizontal line test. And then I already said the word invertible, so might as well just throw that in here. Inverse function. So a one-to-one function is also called an invertible function, and the function that undoes the one-to-one function is the inverse function. By definition, let f be a one-to-one function with domain D and range R, then its inverse function, which we sadly use this notation. Again, I want to remind you that is definitely not an exponent. That's not 1 over f. Please don't make that mistake. It is obviously a terrible notation adopted throughout history, at least for the last few hundred years. I completely detest it, but it is just a notation we have adopted, and I can't change it. I'm just one person. So back to work here, right? Then its inverse function, again, which is denoted f inverse, has domain R and range D. So the range and domain swap positions when you talk about a function versus its inverse. And whatever was in the domain of f now is in the range of f inverse. And whatever was in the range of f is now in the domain of f inverse. That's how that works. You should also recall the inverse function property, which basically says that if you compose a function with its inverse, they undo each other. So f inverse of f of x will return x. F of f inverse of y will return y. And that's how that works. So let's go ahead and jump into some examples, because I don't think I have anything else here. So let's jump into some examples of finding equations of the inverse. So there is a very tried and true method to algebraically find the inverse of a one-to-one function. However, there's a little bit of a notational flaw in this method. So I want to talk about that at the end. But the idea is to swap out f of x for y. That's the first thing we're going to do. In fact, maybe I should go ahead and do that while I state it, right? So if I'm going to find the inverse of this function down below, I'll start by swapping out f of x for y. Everybody's used to that. Then you solve the equation. Instead of for y, you solve it for x. So you do the opposite of what normally you would do. So we solve for x here. So this is probably, I would say, the hardest part for most students. Get rid of those denominators. That's probably the easiest thing we could do. So multiply both sides by x minus 3. In fact, maybe I should write this in here. This implies, and I'm going to multiply both sides by x minus 3, so that you get y times x minus 3 is equal to 2x minus 1. Now remember, the ultimate goal is to solve for x. So we would like to get terms with x here and then kind of isolate them. So I'm going to go ahead and distribute that y through. So I get xy minus 3y is equal to 2x minus 1. Again, the goal here is to get terms with x on one side and terms without x on the other side. So I will move all terms with x to the left-hand side and all terms with y, or without x, I should say, to the other side. So I have xy minus 2x by subtracting 2x from both sides. And I have a positive 3y minus 1 by adding 3y to both sides. Now I see all my terms with x are on one side. And now I will factor out that x out of the two terms on the left-hand side. And I'm left with a y minus 2. That is equal to 3y minus 1. And finally, divide both sides by y minus 2. When you do that, you get a beautiful x is equal to 3y minus 1 over y minus 2. And now you have actually found, in some way, the inverse function, but unfortunately, notationally, this will not work if you want to graph it. So, at this point, going back to your old algebra courses, you have been taught to swap x and y. So at this point, in a traditional algebra course, you would swap x and y. So this would become y is equal to 3x minus 1 over x minus 2. And at that point, this value of y right there is what we would call f inverse. And so I'm going to go ahead and say this implies that f inverse of x, remember that's not 1 over f, is equal to 3x minus 1 over x minus 2. Now again, there's a significant caveat here. Something that maybe your algebra instructor from the past might have mentioned, but I mention this anytime I teach this topic. That last step is technically only necessary if you're going to graph the inverse function. Performing this final step in applications ruins the meaning of the original variables. So if I was working with an application, I actually would not do that last step. I would avoid swapping variables because in an application, you ruin what the meaning of the variables are. And I'll give an example of that in a few moments. Actually, I just looked ahead and I'm not giving you an example of that. So let me make an example of that right here. So let's suppose that this was the cost of something. I don't really care. That doesn't matter to me, but let's just say it's the cost of renting a car on a per mile basis. So cost per mile. And let's pretend that was your original function, right? 2m minus 1 over, what do we say? Have m minus 3. And then you're told to find the inverse of this. Now remember, this might be cost, and this might stand for the number of miles you drive. Let's just pretend, okay? And somebody says, well, find the inverse because I would like to know how many miles I can drive based upon the cost rather than what is the cost based upon the number of miles. I want to know, in fact, let me write that down. So again, this function gives a cost based upon the number of miles driven. If we're renting a car, let's pretend. But we want to know the number of miles we can drive based upon how much money we have. And I've written that here. We want the opposite situation. That is, we need to know how many miles we can drive based on cost, because maybe we're just limited to how much money we have, right? Nobody has an unlimited amount of money. So we'd like to say, well, all I have is $100. How far can I go? Now we've already found the inverse of this. It's right there. So if you were to find the inverse the same way and then swap letters at the end, it would look like this. Dot, dot, dot. Again, we're finding the inverse here. Finding inverse. And if we go through all that work, found the inverse, and then swapped variables, we would have, well, let's see, we'd have C inverse of m is equal to the fraction 3m minus 1 over m minus 2. This is, again, I wanted to make note here, this is after swapping variables. And this is why I'm just not going to write out the word variables. This is why I'm trying to convince you that swapping variables in applications is a terrible idea. Because remember, the inverse, or the original function, I'll start there, gives a cost based on the number of miles driven. If you drive, let's say, 30 miles, your cost is going to be 30 times 2, or 60, minus 1, which is 59, divided by 30 minus 3, which is 27, whatever that is, right? So that is nearly $2, let's say. It's not a realistic, I didn't say it was realistic, I just made this up. Okay, but that's what the cost would be, that much in dollars. Now you get down here, and the inverse function should say, well, this will give us the number of miles we could drive based upon cost. So the output here should be miles we can drive based upon the cost, right? It's the opposite situation. In the original one, we're plugging in miles and getting out cost. With the inverse, we should be plugging in cost, and getting out miles. But if you look at the letters here, the variables, that is not what they look like they stand for, but that is what they stand for. M in this situation is actually cost. M in this situation is cost. And the reason why is because we swapped variables. It's a really, really terrible idea in applications to swap variables. So the only reason why you truly swap variables is so you can graph inverse functions. But otherwise, there's really no true reason other than if you're doing an online homework or something like that, you have to swap variables. That's just how that is because they've been hard-coded to force you to do that. But all logic and intuition is lost when you find the inverse function and then you swap variables within an application. All intuition is gone. That M is no longer miles, it's money, I guess. And C is no longer cost, it is miles. I couldn't think of a word that started with C for miles. Car miles, I guess. I don't know. Well, now that that is out of the way, let's go ahead and dive into yet another finding the inverse example. So here's a function, and this is what we call a domain restricted function because we've restricted the domain to only allow inputs less than 4. And so in this case, we're asked to find the inverse function of this. Normally this function is not one-to-one actually. And the reason why I say that is because while it is a function, each input definitely goes to its own output and so on and so forth. Each output, on the other hand, does not come from a single input. A simple example of that would be, let's say, something very simple like the output of 0. We can see that it's very easy to see that 0 as an input leads to 0 as an output. But actually, I don't know if you can see it, but 8 as an input will also lead to 0 as an output. So the output of 0 shares 2 inputs. So this is definitely not one-to-one. But because we're doing a domain restriction on this, it will actually, in this specific case, force it to be a one-to-one function. So let's start by graphing it. I just want to showcase that this is one-to-one by graphing this function first. The way that I graph, if you've watched my videos in the past, you probably know that I do not graph the way most people do. I start by just asking, well, what is the y-intercept? And since we're all in precalculus at this point, you should be able to quickly see that that happens at 0, 0. You plug in 0, you get out 0. And then you ask yourself, I already gave the answer to this, but I'm just going to say it again. You ask yourself, when is y equal to that 0 output again? And that occurs when the function output is 0, minus 16x. And of course you could factor that. I'm just quickly doing this. 2x times x minus 8. And you can see that that equation is true at x equals 0, which we've already plotted, and at x equals 8. So this is when this function, these 2 points are when this function g of x hits the x-axis. You also know that it's a parabola opening upward, so there's a vertex somewhere down below here. And that vertex, by the way, occurs halfway between, because it's a hanging chain, the vertex will occur halfway between those two intercepts. So the vertex occurs actually at 4. Now, nobody's really asking us to state that, but it is true. So now you can see that this is definitely not, as written, a one-to-one function because it does not pass the horizontal line test. But if somebody said, you know what though, I don't want you to graph this entire function. I really only want you to graph this function for x to the left of 4 on the number line. So for all this stuff. Well, if that's the case, I can erase all the stuff that occurs before, or I'm sorry, not before, but after x equals 4. And if you look at that domain restricted version of this function, it definitely is 1-to-1 because it passes the horizontal line test. Any horizontal line I draw hits that curve at most once. That's how I know it. So let's go ahead and find the inverse of g of x here. Remember, to find the inverse, you start by allowing y to equal the function, and then you're going to solve for x. My pen is doing some funky stuff today, so I'm going to zoom in. It's a little bit easier to work like that. You're going to solve this for x. Now, a lot of people have a hard time solving this for x, but you've actually been doing this for your entire mathematical career. It's just you haven't seen the pattern, I suppose. That is a quadratic equation. The role of A is being played by 2. The role of B is being played by -16. And the role of C is being played by -y. You could totally do that. It's totally fine. And I could solve this equation for x just by using the quadratic formula. So the quadratic formula gives me the following. X is going to equal a big fraction bar. It's the opposite of b, plus or minus the square root of b squared, which is 256, minus 4ac, all over 2a. You've used the quadratic formula since Algebra 1, so this should not be a big surprise. Probably the hardest thing for people to realize is that they can actually have variables within their quadratic formula. When I teach Algebra 2, I use these styles of equations, not all the time, but I do it a few times in Algebra 2, and then I start using it a lot in Trig because I want students to get used to this idea. So you should be able to do that. And of course, this just implies that x is going to be 16 plus or minus the square root of 256 plus 8y all over 4. 8 goes into 256, but unfortunately the square root of 8 is not a pretty number, so I'm going to divide 4 out of the radicand there. So it's 16 plus or minus the square root of 4, I'll write it that way, times the square root of, well, 256 is, let's see, 4, 16, 64 times 4. So 64. Double check my math. Yes, that's right. Plus 2y. All over 4. And you know square root of 4 is 2. So I'm going to break this up. This is going to be 4 plus or minus 1/2 square root of 64 plus 2y. Let me clean up that y. It's terrible. So we get down to this. Now remember, the first step was really to swap. The second step was to solve for x. And so we've solved for x. We get 2 possible solutions, which is illegal. You cannot have 2 solutions for x. You only can have 1. If you have 2, then it's not a 1-to-1 function. Luckily, we've been told from the get-go, climbing up to the top, that x must be strictly less than 4. So our answer, x, cannot be at 4 plus something. It has to be 4 minus something. That's the big hint. That our answer right here cannot be 4 plus 1/2 root 64 minus 2y, but instead 4 minus, because again, the x value is less than 4. So I'll write that in. And there we go. Due to the domain restriction, that x being less than 4, we know that x must be 4 minus 1/2 square root of 64 plus 2y. And now we swap, finally, the x and y values. And I'll go ahead and write it this way. But again, remember, if this was an application, I would probably not want to swap these because it is the variables lose their meaning. However, if you're using an online homework system, you'll always have to swap them because that whoever coded that will expect that. And finally, you probably should mention that this is g inverse of x. That was the name of the function g. So g inverse of x is 4 minus 1/2 square root of 64 plus 2x. And you're done. That is the inverse of the domain restricted function g of x. So it looks like a lot of work in there, but in reality, it's not too terrible. You just have to remember a couple things. First of all, you have to remember that you can actually build a quadratic equation with variables in it. And two, you have to remember your domain restriction. Now, the last kind of review topic for inverse functions that is important, in my opinion, is graphing the inverse of a one-to-one function. Now, this is honestly very fast for most students. So the way that I'm going to do this is use technology. But to graph the inverse of a given one-to-one function, either reflect the function about y equals x, because you're just swapping x and y values. A reflection about y equals x gives you the graph of the inverse. Or another thing you can do is plot the points x comma y that occur on the original function in the opposite order as y comma x. Again, for the same exact reason, because the inverse of your function just swaps the x and y values for graphing purposes. So let's go ahead and take a look at this example. Use technology to draw the following function, or give a graph of the following function. If it is one-to-one, then graph its inverse. If it's not one-to-one, build a domain restriction and then graph the inverse of the resulting domain restricted function. Now I'm in my handy dandy Desmos graphing screen here, and I'm just going to graph, I think we called it f of x, and it's the cubed root, which you could actually type in a cube root, I think, in Desmos, but I'm going to do it as a 1/3 power. So this is x squared plus 1 to the 1/3 power. I'm almost positive you can actually do a cube root otherwise. Now you can see that that function right there is definitely not one-to-one. And the reason why I say that is because I don't want, I'll do a, y equals a, and let's add a slider to a equals 1. Okay, and that's all I need. So because while there are horizontal lines that down here that don't even hit the graph, that's perfectly fine. Once you get to about here, here's a horizontal line that hits the graph more than once. Once you get that, you know that function's non-invertible. So we need to go ahead and domain restrict this function. It is actually your choice. If somebody doesn't tell you how to domain restrict the function, you can restrict the domain any which way you want. I'm going to go ahead and domain restrict this for x values greater than 0. So that gives me what looks to be a one-to-one function. Notice, by the way, I try to teach you a little bit of Desmos as we move forward. If you want to do a domain restriction for a function, you could, at the end of the function, use braces. And in the brace, you would just give the domain restriction. X must be greater than 0. Or in this case, you could have done x must be less than 0. That is also a perfectly fine domain restriction. Another one you could technically do here that would still yield a one-to-one function is to restrict x between 0 and, let's say, 3. That's domain restricted and it is invertible. So it just depends. I'm just going to grab the biggest region that is still one-to-one. So there we go, from 0 to infinity. So let's go ahead and showcase how to graph this by hand. Well, okay, I'm going to copy this graph by hand. So it goes through 0, 1, and then kind of has this really bowed upward, and then has an inflection point and bows downward. So I'm going to go back to my by hand graph, and then I'm going to showcase how to do this. So as I have on a different screen in front of me, our graph goes through 0, 1, and then you can actually go in and try to find better values. I'm not going to be able to do that very easily here. So instead, I'm just going to go ahead and try to copy it out. It looks something like this. This is actually a pretty good graph. I'm thinking about it. So now I want to reflect this curve about the line y equals x. It's probably going to be the best way to go about this. And the more I thought about it, the more I was like, you know what? We probably should graph y equals x as well, just to see what that looks like. Oh, and you have this great intersection point. It occurs at 1 point. Let's just call that 1.5, even though it's not. So they intersect at 1.5 comma 1.5. So on my background graph that I'm drawing by hand, that's what I'm going to put in here. And you can see that's kind of what I've done here. It's supposed to be y equals x, and it actually is, because this goes through 0, 0, which y equals x goes through, and 1.5 comma 1.5, which y equals x goes through. It's just that the scale is kind of weird, so it doesn't look like a 45-degree angle with the x-axis, but we're going to pretend as though it is because the scale is kind of awkward here. However, this will allow me to go ahead and graph this the inverse of this function. The first thing I'm going to do, and maybe I'll do this graph in green, is note that 0 comma 1 is on the graph the original function, so 1 comma 0 will be on the graph of the inverse function. They're going to meet right at that point right there. Remember, the scale on this is really terrible. So I'm just letting you know the scale is pretty bad, but I want to get this as reflected as possible. Trying not to... There we go. So this, if there was a mirror image about this line y equals x, and unfortunately, if it's not perfect, a perfect mirror image on my end, just because of the fact that it is kind of askew. But if it wasn't askew, that would be a perfect reflected mirror image about the line y equals x. And just to showcase that, here is the inverse function in green in Desmos, y equals x in blue, and the original function domain restricted in red. If you're wondering how I found the inverse function, I didn't. I did exactly what I said you should do, which is I solved for x. No, I basically swapped x and y is basically what I did. I swapped x and y here and said, instead of looking at y equals x squared plus 1 to the 1/3, I want to graph x equals y squared plus 1 to the 1/3, because when you swap x and y variables, that's what you're doing for graphing. And then instead of x being greater than 0, I did y being greater than 0. And that gives me the visual of the inverse function. Now, in the question itself, they didn't ask me to find the inverse function. And you can see that, right? Use technology to draw a graph. If it's 1-to-1, graph its inverse. If not, restrict the domain, and so on and so forth. So really the point of this example was to just find the domain restriction. But finding the inverse of this is not terrible. I'll leave it for you. Go ahead and find the inverse, pause the video right now, and then when we come back, I'll just show you really quickly what the inverse is. And there you have it. That would be the domain restricted inverse function, where it's the positive square root because you want all your values to be positive. All right, that's it for this section. I hope this is somewhat of a review for you and that it was somewhat enlightening. If you found that this material was well beyond your skill level, you might want to search for full-on lecture videos on inverse functions, 1-to-1 functions, finding the inverse of the function mechanically, drawing inverses of functions, all the time.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much, that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.